Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have a right triangle ABC. This is the right triangle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. Inside the right triangle ABC, we have this small circle and this semicircle, and our mission is to find out the radius of this small circle. So first of all, we will implement the Pythagoras theorem in this big triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC. The square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. So I will write it down. The right triangle ABC, here by PT is a relation from Pythagoras theorem. So AC square equals to AB square plus BC square. So I'll write it down. AC square, that is the square of the hypotenuse, must be equal to AB square plus BC square. The hypotenuse AC is the missing side, so limit as it is, AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So now we found out that AC square equals to 63 plus 64, that is 100. So AC square equals to 100. We take out of this equation and we get that the missing side, the hypotenuse AC equals to the square root of 100, it is 10. So the length of the hypotenuse AC is 10, so I'll write it down. AC equals to 10. We define the center of this small circle, this point is point P. We define the center of this big semicircle, this point is point Q. And here we define the point of tendency of tangent AC with this semicircle. This point is point H. So here we can implement rule 2. One, because if we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AB and tangent AH. According to rule 2, they are equal to each other. That is to say, AB equals to AH. Repeat again. According to rule 2, tangent AB equals to tangent AH in its length, but AB is 6 according to what is given as the equation. So we can write here that AB equals to 6, and for this equation 6 equals to AB equals to AH, we derive that the length of side of tangent AH is also 6. So AH equals to 6, so yeah, this is side tangent AH. That equals to 6 units in its length. So I write it down. We have already found out that the length of the hypotenuse AC is 10, AH is 6, therefore the missing side HC must be equal to AC minus AH. Again, AC minus AH equals to the missing side HC. So HC in total equals to AC, that is 10, minus AH, that is 6. 10 minus 6 is 4, so the rest inside HC is 4. HC equals to 4 units in its length. In the next step, we join points Q and H together by side line. Point Q is the center of this semicircle, point H is a point on the semicircle itself, therefore QH is the radius of this semicircle. We define the radius of this semicircle as B, therefore QH equals to B, according to our definition. Here we can implement rule 1, because we have here the radius QH is drawn to point H, it is the point of tendency of tangent AC with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay. So here, this is angle C. Angle C is a common angle that belongs both to the big right triangle ABC, and angle C also belongs to the right small triangle HQC. So we'll define the size of this angle C as alpha. And we focus on the right small triangle QHC. On the right small triangle QHC, this angle equals to alpha, this angle equals to 90 degrees, and therefore this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, we'll continue, we'll focus on the big right triangle ABC. On the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus alpha. In the next step, we prove that the big right triangle ABC, this is the big right triangle ABC, is similar to the small right triangle HQC. We already found out that angle alpha is a common angle that belongs to both triangles. It belongs to the small right triangle HQC, and it also belongs, of course, to the big right triangle ABC. So we prove that the big right triangle ABC is similar to this small right triangle HQC. So write it down. We prove that the big right triangle ABC is similar to the small right triangle HQC. So why the big right triangle ABC is similar to this small right triangle HQC? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABC in the right big triangle ABC, and it is equal to this angle. This is actually angle QHC in the small right triangle QHC. So repeat again. Angle ABC in the big right triangle ABC equals to angle QHC in the small right triangle HQC. They are both equal to 90 degrees, therefore they are equal to each other. In addition, as I already mentioned before, this is angle alpha, that is a common angle. It belongs both to the big right triangle ABC and it of course belongs also to the right small triangle HQC. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. So if we relate to this angle alpha as it belongs to the big right triangle ABC, it will be defined as angle ACB, and it equals to itself. So if we relate to this angle alpha as it belongs to the small right triangle HCQ, it will be defined as angle HCQ. Repeat again. This equation means that angle alpha equals to itself. We just called to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually, this is angle BAC, the big right triangle ABC. And it is equal to this angle, that is actually angle HQC. This one, right triangle HCQ. Repeat again. Angle BAC in the right big triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually proved that all the triangles in the right big triangle ABC are correspondingly equal to all the triangles in this small right triangle HQC, and therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. So we found out that the big right triangle ABC the big right triangle ABC is similar, this is the sign of similar, to the right big triangle HCQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB, the big right triangle ABC, over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC. This is side BC in the big right triangle ABC over side edge C in the small right triangle edge CQ. Repeat again. We derive that side AB, the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC, the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of this semicircle, that is equals to B according to our definition, and it is equals to BC. BC is 8 according to what is given us the question, over HC. We already found out that HC equals to 4. HC equals to 4. So in conclusion, we actually found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So in conclusion, we actually found out that 6 over B equals to 2. Here we multiply this equation by B, and we get that 6 equals to 2B. 6 equals to 2B. We divide this equation by 2, and finally we get that the visible radius of the semicircle B is equals to 6 over 2, that is 3. We actually found out that the radius of this big semicircle B equals to 3 units in its length. So I write it down. B equals to 3. Here, line segment QB is also defined as the radius of this semicircle, and therefore it is equals to 3 units in its length. So I write it down. QB equals to 3. This is the radius of the semicircle. We define the point of tendency of tangent AB with this small circle. This point is point N. In the next step, we join points P and N together by a straight line. PN is of course the radius of this semicircle because it starts from point P, that is the center of this small circle, and ends at point N, that is the point of the small circle itself. This is exactly the definition of a radius. Therefore, Pn is the radius of this small circle. We define the radius of this small circle Pn as A. Therefore, Pn equals to A. Our mission is to find out the value of A, that is the radius of this small circle. Here we can implement rule 1 because we have here the radius Pn that is equals to A is drawn to point N, that is the point of tendency of tangent AB with this small circle. And whenever your radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius NP according to rule 1. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. We will define the point of tendency of tangent AC with this small circle, this point, as point K. We join points P and N together, we join points P and K together by straight line. PK is the radius of this small circle, that equals to A. Again, we have the radius PK is 1 to point K, and therefore according, this is the point of tendency of tangent AC with this small circle, therefore according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. we define the point of tendency of this small circle with this semicircle, or the touching point. This point is point S. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you draw two tangents to that circle. So here, this is the common external point P. From this common external point P, we draw two tangents to this circle, tangent PA and tangent PB. In this way, we created angle APB. Again, angle APB was created by drawing two tangents from this common external point P to this circle, tangent PA and tangent PB. Okay. Then the angle that will be created between the two tangents, angle APB, this is angle APB, that was created by drawing the two tangents PA and PB. So this angle APB, according to rule 15, the angle that will be created between the two tangents, that is angle PAB, its angle bisector must pass through the center of the circle. Okay, so the angle bisector of this angle PAB must pass through point O, that is the center of this circle. Okay, so actually the angle bisector of this angle PAB is OP. And you can see that OP passes from point O, that is the center of the circle. Angle bisector OP bisects angle PAB into two halves. The size of angle PAB in total is 2 theta, and the angle bisector OP bisects angle APB, that is 2 theta into 2 halves. Each half equals 2 theta. This is angle APO, that is equals to theta, and the other half is angle OPB, that is also equals to theta. So according to this rule of rule 15, whenever for a common external point P, we draw two tangents to this circle, tangent PA and tangent PB. In this way, we created angle APB. The angle bisector of this angle APB must pass from point O, that is the center of the circle. So the angle bisector OP bisects angle APB to 2 halves. Each half equals to theta. Okay. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, here, if we focus on this common external point A, from this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. In this way, we created here, this is angle A that was created by drawing two tangents to this small circle, tangent AN and tangent AK. And according to rule 15, the angle bisector of this angle A, must pass through point P, that is the center of this small circle. Again, according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this small circle. So I will draw the angle bisector of this angle A. Angle bisector of angle A must pass through point P. can see here that the angle bisector of angle A pass from point P, that is the center of this small circle. If we define the size of angle A as 2 theta, then the angle bisector PA of angle A bisect angle A into 2 halves. Each half must be equal to theta. So this is the first half, and this is the second half of angle A. In total, angle A equals to 2 theta, therefore each half of angle A equals to theta. You can see here that the angle bisector PA that passes through the center of this small circle, that is point P, this angle bisector PA bisects angle A into 2 halves. Each half equals to theta. So, in conclusion, we can find out that angle bisector of angle A pass through point P. So I already know angle bisector of this angle A pass through point P, that is the center of this small circle. So I already know, actually found out that according to rule 15, actually, angle bisector of angle A pass through point P, that is the center of this small circle. Likewise, if we continue to focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents to this semicircle. We have tangent AB and we have tangent AH. Actually, by drawing the two tangent AB and AH towards this semicircle, we created the angle A. So angle A is created by drawing the two tangents AB and AH towards this semicircle. Therefore, we can implement the rule 15. According to rule 15, the angle bisector of this angle A, must pass from point Q, that is the center of this semicircle. Repeat again, the angle bisector of this angle A that was created by drawing two tangents, tangent AB and tangent AH towards this semicircle. This angle bisector of angle A must pass from point Q, that is the center of this semicircle. So I will draw the angle bisector of this angle A, and according to rule 15, angle bisector of this angle A must pass from point Q. So you can see that angle bisector of angle A passes through point Q, that is the center of this semicircle, exactly according to rule 15. So in conclusion, we can write down that angle bisector of the same angle A passes through point Q, that is the center of the semicircle. So already now, actually found out that the angle bisector bisector of the same angle A pass for point Q, that is the center of this semicircle. So in conclusion, we can say that angle bisector of this angle A passes through point S and through point Q. And of course, that angle bisector of this angle A must pass through point A. It is trivial, but I must say it. Again, the angle bisector of this angle A must pass through point A. So it is known angle bisector of the same angle, angle A, passes through point A. So in conclusion, can I know that the angle bisector of this angle, angle A, passes through points A, S, A, P, and Q. Again, the angle bisector of this angle A passes through points A, P, and Q. So write it down. Actually, found out that angle bisector of this angle, angle A, passes through points A, P, and Q. And we also know that the angle bisector of any angle is a straight line, of course. Therefore, we can write down that line segment APQ is a straight line. Okay? Because of the fact that angle bisector of A is a straight line, therefore line segment APQ, this line segment APQ must be also a straight line. Or we can say also that all the 3 points A, P, and Q, they are located on the same straight line. It is exactly the same if we say that line segment APQ is one straight line. Okay? APQ is one straight line. Line segment APQ is a straight line or one straight line. Okay, line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. AQ is a straight line. And therefore, shape AQB is a right angle. Again, shape AQ is a right angle because AQ is a straight line. AQ is actually the hypotenuse of the right angle AQB. And this is angle theta. That is a common angle. It belongs both to the right big triangle AQB, and this angle theta also belongs to the small right triangle ANP. Okay, so if you focus on the small right triangle ANP, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. Likewise, if you focus on the right big triangle ABQ, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. In the next step, we will prove that the right big triangle ABQ is similar to this right small triangle and ANP. So that is known. We prove that the right big triangle ABQ is similar to the right small triangle ANP. So those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. So actually, this is angle ABQ, the right triangle ABQ. And it is equal to this angle, this is actually angle ANP, the small right triangle APN. So repeat again. We actually found out that angle ABQ in the right big triangle AQB equals to angle ANP in the right big triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle, it belongs to both triangles, it belongs to the small right triangle ANP. Angle theta of course belongs to the right big triangle ABQ. So we can write down that angle theta equals to itself as a common angle that belongs to both triangles. So if you relate to angle theta as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And it is equal to itself. So if we relate to this angle theta as it belongs to the small right triangle ANP, it will be defined as angle NAP. Again, this equation means that angle theta equals to itself. We just call to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So this is angle AQB. In the right triangle ABQ, and this equals to this angle, it's actually angle APN, the small right triangle ANP. Repeating again, so we found out that angle AQB in the small big triangle ABQ equals to angle APN, the small right triangle ANP. They are both equal to 90 degrees minus theta, therefore they are equal to each other. So if you prove that all the three angles in this big right triangle ABQ are correspondingly equal to all the three angles in this right small triangle A and P. Therefore, those two right triangles are similar to each other according to angle similarity rule. So right now, if we found out that the small right triangle A, the big right triangle ABQ is similar, this is the sign of similar to the right small triangle ANP according to angle similarity rule. And for the fact that the right big triangle ABQ is similar to the small right triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB, the big right triangle ABQ, over side AN in the small right triangle ANP equals to side BQ in the right big triangle ABQ over side NP in the small right triangle ANP. So I repeat again, we derive that side AB, the big right triangle ABQ, side AB, the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the right big triangle ABQ over side NP in the small right triangle ANP. AB is 6 according to what is given as a question over AN. AN is the missing side, so we leave it as it is. Equals to BQ. BQ is 3. This is the radius of the semicircle. That is equals to 3 units in its length. Over N. Over NP. NP is A. So in conclusion, we found out that 6 over AN equals to 3 over A. Here we cross multiply this equation and we get that 6A equals to 3 times AN. Here we divide this equation by 3 and we get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we should find out that the missing side AN equals to 2A in its length. Okay, this is the missing side AN, that is equals to 2A. So AN equals to 2A, AB equals to 6. Therefore, the missing side NB must be equal to AB minus AN. Again, AB minus AN equals to NB. AB is 6, AN is 2A. Therefore, AB minus AN is 6 minus 2A. The missing side NB equals to 6 minus 2A. In the next step, we do a construction, that is to say, from the center of this small circle, that is to say from point P, we draw perpendicular on BQ. Okay. We define the touching point of the perpendicular from point P and BQ. This point is point J. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. By doing this construction, we actually created the quadrilateral NPJB. NPJB. Inside quadrilateral NPJB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 missing angles, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore this 4 missing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBJ we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to this quadrilateral NPBJ as a rectangle because it has 4 right angles. But we also write it down. This quadrilateral NPBJ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBJ, side NP must be equal to the opposite side BJ, but NP is A. It is the radius of the small circle that is equal to A according to our definition. So NP is A, therefore BJ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBJ, side NB must be equal to the opposite side PJ, but NB equals to 6 minus 2A, therefore PJ must be also equal to 6 minus 2A. What is the length of the missing side JQ? From drawing it is very easy to see that JQ equals to BQ minus BJ. Again, BQ minus BJ equals to JQ. So JQ equals to BQ, that is 3, minus BJ, that is 8. So in total, JQ equals to 3 minus 8. So I'll write it down. This side JQ equals to 3 minus 8 units in its length. And in the drawing we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point S. Whenever you have an external notch between two circles or semicircles, you can implement rule 10. So I repeat quickly on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together passes through their touching points. So in the drawing we have two circles. Those two circles touch each other externally at point P. The center of this small circle is there at point M. The center of this big circle is there at point O. And the straight line that connects the centers together is of course the straight line MO. So this straight line MO, according to this rule 10, must pass from point P, that is their touching point. Again, the straight line MO must pass from point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say, they are touching each other externally at point S. And whenever you have an external notch between two circles, you can implement rule 10. The center of this small circle is at point P. The center of this big the center of this big semicircle is at point Q. The straight line that connects the centers together is of course the straight line PQ, and this straight line PQ must pass through point S, that is their touching point. Again, the straight line PQ must pass through point S, that is their touching point, or PSQ is one straight line. Again, PSQ is one straight line. If PSQ is one straight line, it means that PQ must be equal to PS plus SQ. Again, PQ must be equal to PS plus SQ because of the fact that PSQ is one straight line. So I write it down. PQ must be equal to PS plus SQ. So PQ equals to PS. PS is the radius of this small circle, that is A. A is the radius that we are looking for in this question, plus SQ. SQ is the radius of this semicircle, that is equals to 3. So conclusion, we found out that the length of line segment PQ is 3 plus A. Okay, the length of line segment PQ in total it is 3 plus A. So in the next step I'll copy this green right triangle PJQ in a new page, and we'll implement the Pythagoras theorem on this right green triangle PJQ. The hypotenuse PQ equals to 3 plus A. So that right now found out that the hypotenuse PQ equals to 3 plus A. Side PJ equals to 6 minus 2A, and side JQ equals to 3 minus A. So actually, this is the right green triangle PJQ that I called from the original drawing. I repeat again that the hypotenuse PQ equals to 3 plus A, side PJ equals to 6 minus 2A, and JQ, side JQ equals to 3 minus A. We'll implement the Pythagoras theorem on this right triangle PJQ according to the Pythagoras theorem. In any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in this right triangle PJQ is PQ, therefore the square of the hypotenuse is PQ square. And it must be equal to PJ square plus JQ square. Okay, again, according to the Pythagoras theorem in the right triangle PJQ, PQ square equals to PJ square plus jq squared. PQ is 3 plus A, therefore PQ squared is 3 plus A squared. And it must be equal to PJ squared. PJ is 6 minus 2A, therefore PJ squared is 6 minus 2A squared plus JQ squared. JQ is 3 minus A, therefore JQ squared is 3 minus A squared. In conclusion, we found out that 3 plus A squared equals to 6 minus 2A squared plus 3 minus A squared. We'll open the brackets on both sides of this equation and we get that 3 plus A squared equals to 3 squared, that is 9, plus A squared plus 2 times 3 times A is 6A, and it is equals to 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6 is minus 12, and minus 12 times 2A is minus 24A, plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 times A is minus 6A. So here we have 9 on both sides of the equation, so 9 we get cancelled. And we have also A squared on both sides of this equation, so A squared will also get cancelled. After we cancel those two expressions, we left in this side of the equation only with 6A. In the other side of the equation, we have here 36 plus 4A squared and 24A minus 6A is minus 30A. So if we found out that 6A equals to 36 plus 4A squared minus 30A. Here we subtract 6A from this equation, and we get that in this side of the equation we have if nothing 0, on the other side of the equation we have 36 minus 38 minus 6A is minus 36A plus 4A squared. In conclusion, we found out that 4A squared plus 4A squared minus 36A plus 36 equals to 0. Here we divide this equation by 4, and finally we get that 4A squared over 4 is A squared, minus 36A over 4 is minus 9A, and 36 over 4 is 9. In conclusion, we found out that A squared minus A plus 9 equals to 0. So actually, this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. And then in the general formula for quadratic equation, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say, a squared minus 9a plus 9 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. The variable that we are looking for in our specific quadratic equation is a, so x equals to a. Now the only thing that is left to do is to put the data of our specific quadratic equation in this general formula for x, and we find out the value of a, because x equals to a. A is the radius of the small circle, that is the radius that we're looking for in this question. So we'll put the data inside this general formula, and we find out the value of the values of a. We do it now, and we get that x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is 9, therefore b squared is 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c, that is c is 9. So minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So in conclusion we found out that a equals to 9 plus minus, inside the root we have 81 minus 46. 81 minus 46 is 45 over 2. So here we have two solutions that are possible for a. The first solution for a is that a, that is the radius of the small circle, equals to 9 plus square root of 45 over 2. 9 plus square root of 45 over 2, it is definitely greater than 3. A can never be greater than 3. The radius of the small circle the radius of this small circle can never be greater than 3. Why? Because of the fact that this small circle is definitely smaller than the big semicircle. And we know that the radius of the big semicircle is 3. Therefore, the radius of this small circle must be less than 3. So, the solution for a that is greater than 3, it is incorrect solution, so we'll cancel the solution, and we're left only with the second solution that is possible for a. The second solution that is possible for a is a equals to 9 plus minus square root of 45. We have square root of 45. 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So a, the radius of the small circle, that is the radius that we are looking for in this question, equals to 9 minus, again the second solution that is possible, a equals to 9 minus square root of 9 times 5 over 2. The square root of 9 is 3, so in total this expression equals to 3. Inside the root we left only with 5 divided by 2. So according to the solution, the length of the radius a of the small circle, it is equals to 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, it is equals to 1.146 units in its length. Repeat again, actually we found out that the radius of this small circle, the radius a, is equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, the radius of this circle a equals to 1.146 units. Okay? So in the next step, I will summarize the lecture. In this lecture, we found out the radius of this small circle. So in the drawing, we have the big triangle ABC. This is again ABC. This is a right angle. We know that side AB, this triangle ABC equals to 6 units in its length. Side BC equals to 8 units in its length. Inside this big right triangle ABC, we have this small circle, and we have also this big semicircle. Our mission is to find out the radius of this small circle. So in the first step, we implemented the Pythagoras theorem on this big right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle ABC, it means that the square of the hypotenuse is AC, therefore the square of the hypotenuse is AC square, and AC square must be equal to AB square plus BC square. Okay, again, according to the Pythagoras theorem in the right triangle ABC, AC square equals to AB square plus BC square. AC is the missing side, therefore we limit as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 square, that is 36, plus BC square. BC is 8, therefore BC square is 8 square, that is 64. So in total, AC square equals to 36 plus 64, that is 100. AC square equals to 100, we took out of this equation, and finally found out that the missing hypotenuse AC is equals to the square root of 100, that is 10. The hypotenuse AC of the right triangle ABC equals to 10 units in its length. Here we define the center of this small circle, this point is point P. We define the center of this big semicircle, this point is point Q. Here, if we focus on this common standpoint point A, from this common standpoint point A, we have two tangents to this semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. Okay, AB equals to AH. Okay, again. According to rule 2, the length of tangent AB is equal to the length of tangent AH. But it is given as the equation that AB equals to 6. And from this equation, 6 equals to AB equals to AH, we derive that the length of AH is 6. This line segment AH equals to 6 units in its length. So, we have already found out that the hypotenuse AC of this right triangle ABC equals to 10 units in its length, AH equals to 6, and therefore the missing line segment HC must be equal to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus AH, that is 6. So in total, HC equals to 10 minus 6, that is 4. And again, so in conclusion, we found out that HC equals to 4 units in its length. In the next step, we join points Q and H together by a straight line. Point Q is the center of this semicircle, point H is the point on the semicircle itself, therefore QH is the radius of this semicircle. We define the radius of this semicircle as B, therefore QH equals to B. And we have the radius QH is drawn to point H, that is the point of tendency or tangent AC with this semicircle. Whenever we have a radius that is drawn to the point of tendency, then tangent QH must be, then tangent AC must be perpendicular to the radius HQ. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to rule 1. Okay? So, in the next step, we actually proved that the right big triangle ABC is similar to the right small triangle HQC. We defined this angle C as alpha. So in the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees. That is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees according to what is given as the question. Therefore, this third missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the right big triangle ABC is similar to this right triangle HQC. So, why those two triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle that belongs to both triangles. So I can write down that angle alpha equals to itself. It's a common angle that belongs to both triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So if we prove that all the triangles in the right big triangle ABC are correspondingly equal to all the triangles in this right triangle HQC. Therefore, those two right triangles are similar to each other according to angle similarity rule. So if again, we actually found out that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle HCQ according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB 6, HQ is the radius of this semicircle that is equal to B according to our definition. BC is 8 according to what is given as the question. And finally, HC is 4. In conclusion, we found out that 6 over B equals to 8 over 4. 8 over 4 is 2. Therefore, we found out that 6 over B equals to 2. We multiplied this equation by B and found out actually that 6 equals to 2B. We divided this equation by 2 and finally found out that the missing radius of the semicircle B equals to 6 over 2, that is 3. So the radius of this big semicircle B equals to 3 units in its length. In the next step, I presented to you Rule 15 and we implemented Rule 15 in our drawings. So I'll repeat quickly on Rule 15. According to Rule 15, if from an external point of a circle we will draw two tangents to that circle, here. This is the common external point, point P. From this common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. this way, by drawing two tangents from this convex point P to this circle, we created here angle APB. This is angle APB. Then the angle that will be created between the two tangents, this is actually angle APB. This angle APB, its angle bisector must pass through the center of the circle. The angle bisector of this angle APB must pass through point O, that is the center of this circle. So whenever you draw two tangents from a common point to the circle, then you will create an angle, and the angle that was created, its angle bisector must pass through the center of the circle, that is, in this case is point O. Or, in other words, OP is the angle bisector of angle APB. So, if the size of angle APB is 2 theta, then the angle bisector OP bisects angle APB into 2 halves. Each half equals to theta. Okay? So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if you focus on this common standpoint, point A, from this common standpoint, point A, we have two tangents to this small circle, tangent AK and tangent AN. By drawing those two tangents, we get here angle A. And according to rule 15, the angle bisector of this angle A must pass from point B, that is the center of this small circle. Okay? Actually, the angle bisector PA bisects angle A into 2 halves. If the size of this angle A is 2 theta, then the angle bisector PA bisects angle A into 2 halves. Each half equals to theta, as you can see here. So in conclusion, we can write down that the angle bisector of this angle A passes from point B, that is the point, that is the center of this small circle, according to rule 15. Likewise, we'll continue to focus on this convex standpoint, point A. From this convex standpoint, point A, we have two tangents to this semicircle. We have tangent AB, and we also have tangent AH. So by drawing the two tangents AB and AH to this semicircle, we get here angle A. This is the same angle A. According to rule 15, the angle bisector of this angle A must pass from point Q, that is the center of this semicircle. Or QA is the angle bisector of this angle A. So as I mentioned before, if the size of angle A is 2 theta, then QA bisects angle A into 2 halves. Each half equals to theta. So in conclusion, we can write down that the angle bisector of angle A passes from point Q. Okay, okay, again, we should have found out that angle bisector angle bisector of angle A passes from point P, and just right now found out that angle bisector of the same angle A passes also from point Q. Again, the angle bisector of this angle A passes from point P and from point Q according to rule 15. In addition, it is very clear and it is obvious that the angle bisector of this angle A must pass also for point A. Okay, repeat again. Angle bisector of angle A must also pass for point A. So in conclusion, we can say that angle bisector of this angle A must pass through points A, P, and Q. Repeat again. Angle bisector of angle A passes through points A, P, and Q. Okay? So, angle bisector of any angle, it is absolutely a straight line, and therefore APQ are located on the same straight line, or line segment AQ is one straight line. Line segment APQ is one straight line. Repeat again. Here we have line segment APQ is a straight line or one straight line, it is the same. If line segment APQ is one straight line, it means that AQ is also a straight line. And therefore, shape AQB is a right triangle. Why? Because AQ is a straight line, therefore AQB is a right triangle. And in the right triangle AQB, we have, this is angle theta, but this angle theta also belongs to the small right triangle APN. In conclusion, we found out that angle theta is a common angle that belongs both to the big right triangle AQB, and this angle theta also belongs to this small right triangle APN. So angle theta is a common angle that belongs to both triangles. So in this small right triangle APN, this angle equals to theta, this angle equals to 90 degrees, therefore this missing third angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, if you focus on the big right triangle AQB, this angle equals to theta, this angle equals to 90 degrees, therefore this third missing angle must be equal to 90 degrees minus theta. In the next step, we proved that the small right triangle ANP is similar to the big right triangle ABQ according to angle similarity rule. So repeat again, why those two right triangles are similar to each other. First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles, so we can write down that angle theta equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So we should prove that all the angles in the big right triangle ABQ are correspondingly equal to all the angles in this small right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I'll repeat again. We actually found out that the big right triangle ABQ is similar, this is the sign of similar, to the small right triangle ANP according to angle similarity rule. And from the fact the triangle ANP is similar to the right big triangle ABQ, we derive that the following relationship exists between their sides. We derive that side AB of the big triangle ABQ over side AN of the small triangle ANP equals to side BQ with the big right triangle ABQ over side NP in the small right triangle ANP. I'll repeat again. We will derive that side AB in the right big triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. AB6, AN is the missing side, so we leave it as it is. BQ equals to 3, it is the radius of the semicircle, that is equals to 3. NP is the radius of this small circle, that is A is the radius that we are looking for. So if we're going to find out that 6 over AN equals to 3 over A. Here we can multiply this equation and finally found out that 6A equals to 3AN. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3, that is 2A. So this is the missing side AN, this equals to 2A. According to what is given as the equation, AB equals to 6. We just right now found out that AN equals to 2A, Therefore, the missing side A and B must be equal to AB minus AN. AB minus AN. AB is 6, AN is 2A, so in total, the missing side and B must be equal to 6 minus 2A. In the next step, from the center of this one circle, that is to say from point P, we draw perpendicular on BQ. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point J. By doing this construction, we get the quadrangle NPBQ. Inside this quadrangle NPBQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 facing angle, in total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrangle NPBJ, we have 4 right angles. And according to rule 5, any quadrangle that has 4 right angles must be at least a right angle if not a square. So we relate to this quadrangle NPBJ as a right angle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBJ, side NP must be equal to the opposite side BJ. But NP is A, therefore BJ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBJ, side NB must be equal to the opposite side PJ. But NB is 6 minus 2A, therefore PJ must be also equal to 6 minus 2A. What is the length of the missing side JQ? From the drawing, it is very easy to see that JQ equals to BQ minus BJ. Again, BQ minus BJ equals to JQ. So JQ equals to BQ, that is 3. It is the radius of the semicircle, minus BJ, that is A. So in total, JQ equals to 3 minus A. Now, we have an external length between this small circle and the big semicircle. That is to say, they are touching each other externally at point S. And whenever we have an external length between two circles, you can implement rule 10. Pick rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together must pass through their touching points. And in the drawing we have two circles, and they touch each other externally at this point, point P. The center of this small circle is here at point M. The center of this big circle is here at point O. And the straight line that connects the centers together is of course the straight line MO. And according to this rule, rule 10, the straight line MO must pass for the touching point, that is point P. Again, the straight line MO must pass for the touching point, that is point P. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing we have an external length between this small circle and the big semicircle. That is to say they are touching each other externally at point S. So according to rule 10, the center of this small circle is at point P. The center of this semicircle is at point Q. The straight line that connects the centers together is of course the straight line PQ. And this straight line PQ must pass through point S. Again, the straight line PQ must pass through point S, or PSQ is one straight line, and because of the fact that PSQ is one straight line, of course PQ must be also a straight line. But what is the length of PQ? The length of PQ must be equal to PS plus SQ. Again, PQ equals to PS plus SQ only because of the fact that PSQ is one straight line. Therefore PQ equals to PS plus SQ. So PQ equals to PS is the radius that we are looking for, that is A, is the radius of this small circle, plus SQ. SQ is 3. So in total, PQ equals to A plus 3. Here, PQ equals to A plus 3. In the next step, I copied the right green triangle PJQ in a new page and implemented the perpendicular theorem of this green right triangle PJQ. Actually, this is the green right triangle PJQ that I copied from the original drawing. We just right now found out then the hypotenuse PQ of this right triangle PJQ equals to 3 plus A, PJ equals to 6 minus 2A, 6 minus 2A, and JQ equals to 3 minus A. According to the Pythagoras theorem, in this right triangle PJQ, PQ square equals to PJ square plus JQ square. Again, PQ square equals to PJ square plus JQ square. And again, PQ square equals to PJ square plus JQ square. PQ is the hypotenuse that is 3 plus A, therefore PQ square is 3 plus A square. PJ is 6 minus 2A, therefore PJ square is 6 minus 2A square plus JQ square. JQ is 3 minus A, therefore JQ square is 3 minus A square. In conclusion, we found out that 3 plus A square equals to 6 minus 2A square plus 3 minus A square. Here we open the brackets on both sides of this equation and finally found out that 3 plus A square equals to 3 squared, that is 9, plus A square, plus 2 times 3 times 8, that is 6A, and it is equals to 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, times 2A, 12 minus 2A is minus 24A. Okay? Minus 24A. We have also here 3 minus A square equals to 3 square, that is 9, plus A square, minus 2 times 3 times 8, that is minus 6A. So here we have 9 on both sides of the equation, so 9 will get cancelled, and we have also A square on both sides of the equation, so A square also will get cancelled, and so we cancel those two expressions. In this side of the equation we left only with 6A. In the other side of the equation we have 36 plus 4A square minus 24A minus 6A is minus 30A. So in conclusion, we found out that 6A equals to 36 plus 4A square minus 30A. Here we subtracted 6A from this equation and finally found out that in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 36 plus 4A square and minus 38 minus 6A is minus 36A. So in conclusion we actually found out the 0 equals to 36 minus 36A plus 4A square. Here we divided this equation by 4 and finally found out that 4A square over 4 is A square, minus 46A over 4 is minus 9A, and 36 over 4 is 9. So in conclusion, we found out that A square minus 9A plus 9 equals to 0. So this is actually a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. If a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus root of b squared minus 4 times ac over 2a. In our specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. And the variable that we are looking for in this equation is a, so x equals to a. So the only thing that is left to do is to put the data of our specific quadratic equation in this general formula for x, and we will find out the values of a, because x equals to a. So we did it, and we found out actually, again, x equals to a, so a equals to minus b. B is minus 9, therefore minus b is minus 9, that is plus 9, plus minus square of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a. A is 1, so minus 4 times 1 is minus 4, times c, that is 9. Minus 4 times 9, it is minus 36, divided by 2a. A is 1, so 2 times 1 is 2. Inside the root, we left only with 81 minus 36. So we found out that a equals to, inside the root we have 81 minus 81 minus 36 is 45. So in other words, we left only with 45 divided by 2. So we have here two solutions that are possible for A. The first solution for A is that A equals to 9 plus square root of 45 over 2. But because of the fact that this expression 9 plus square root of 45 over 2, it is definitely greater than 3, and we have already found out that the radius of the big semicircle equals to 3. And from the dome it is very easy to see that the semicircle is smaller than this small circle is smaller than the semicircle. Therefore, the radius of the small circle must be shorter than the radius of the big semicircle. Therefore, the radius of this small circle must be less than 3 units. And because of the fact that here the radius A of the small circle is greater than 3, this solution is an incorrect solution. We cancel the solution and we're left only with the second solution, that is for A. The second solution for A is A equals to 9 minus, we substitute 45 by 9 times 5 divided by 2. The square root of 9 is 3. In other words, we left only with square root of 5. So conclusion, we found out that the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, it is equal to 1.146 units. I repeat again, we actually found out that the radius A of this small circle equals to either 9 minus 3 times square root of 5 over 2 units, or in terms of numbers, the radius of this small circle A equals to 1.146 units. Okay, thank you very much.